All right, I'd like to welcome you to the Ecosystem Indicators Workshop. Thanks everyone for coming, and I'd really like to thank a bunch of you for making this possible. This workshop came about because a number of you raised some concerns about disturbing trends in salmon populations within Puget Sound. You were concerned about the forecast being wrong, and you were concerned about a lack of indicators measured within Puget Sound to basically improve those forecasts. And so, by your stirring up trouble, got John Stein's attention, and several months later now, we've got this workshop. So thank you. And what we're here for is improving these forecasts. We all want. I think we got some powered forecasting over the last couple of months. We've heard a lot about forecasts. You might be aware through the election, right? So here's the example of a pretty good forecast. This is Nate Silver's work at the New York Times through a bunch of statistical modeling. He did quite a good job at predicting the outcome of the election, as you can see here. Yeah, maybe we can get him to do salmon biology. So we can quibble. This forecast was made a couple of days before the election, but still, pretty much got every state, and the one state that's not on here, Florida, he basically predicted it was going to be a really close call. And last time I checked, which was early morning yesterday, it was still pretty uncalled. Maybe it's done now. Okay, so he predicted that too. So, can we move from predicting the behavior of Joe Biden and all the other voters in the United States to something slightly more serious and pretentious, like the trends and productivity of salmon stocks in Puget Sound and the Salish Sea. So here we got a fundamental question. We got a number of differences between these different aspects of the question is fundamentally the same. Can we use indicators of populations, of other aspects in the environment to predict salmon in the future? And can we do this? Can we build a monitoring program that provides those indicators that we feel are necessary for prediction to do this right? So just to give you a background for myself, I got interested in this when I was pretty early on in my Northwest-centered days. George Pest asked me to help with some data he had on Skagit and Still Squamish rivers, and so he started looking at the predictability of floods for overall adult return rates. And I got interested in other variables, and I can still remember the day when I plugged in a number of different variables. You can see here a relatively simple model of eggs, incubation floods, and a number of oceanographic parameters that went into this day and ocean year factors. And I plugged this in and got a very strong predictable fit. So that was this basically shows you data on a year-by-year basis, and the white dots, those are observations, and the black stars, the big black stars are the predictions, and then the small stars, those are 95% constancy. So I was pretty excited about this. In retrospect, this seems a pretty simplistic model, and I suspect that it's doomed to fail at some point because it's got only so many parameters in it. And so, moving forward, I think we want to think about prediction from a broad set of ecosystem indicators, much along the lines of what Bill Peterson has done for the California current. And so, you can read through this list, and Bill will talk about this in much more detail later this afternoon. We need a lot of parameters to be measured if we're going to take this kind of route. And many of them are inadequately measured within Puget Sound. So for the next couple of days, we got a busy schedule, and we got two big goals. First, we want to discuss the promising indicators predicting adult returns for a number of different salmon species, and we got basically 6 to work with, right? Snook, coho, chum, sockeye, steelhead, and pink, right? And secondly, we want to develop a plan for a collaborative effort to monitor, to share data, and to do some analysis so that we can come away with strong predictions and within a modeling framework for predicting these returns of these stocks in the future. And so basically this workshop, two-day sessions. Today we're really going to try to bring up everybody to speak the same language with respect to what we know about stocks, what we know about indicators, merging them together. And the next day, we're going to be focused on building this plan. So we have a couple breakout sessions in which we're going to focus on those indicators, those promising indicators, figure out where the gaps are, and then sort of from there build a plan for filling those gaps. And then a couple of other sessions tomorrow will focus on developing a strategy for data sharing and for funding this whole effort. So for today, we've got a bunch of talks, and we've got them in 4 different sessions. And what I'd like to do is give the speakers the full time that they have on the agenda. And so save your questions, write them down, save them for the discussions at the end of each session, and that'll make sure we stay on time. And with that, I think I have a few minutes, so I can take a couple questions if you got it. Oh, a couple of housekeeping details. If you haven't turned in your talk speakers, please do so. Provide us Mike Schmidt. He'll come after you. You don't want him coming after you. I'll tell you that. With that, I guess I can take one question or something.
This is one of the ways we're going to use it. This is how we're going to apply this data. We're going to come up with code that's better forecast.
Thank you. All right, with that, sure.
Correigh, is there like a workshop product where you can have like a summary or outcome of the abstract?
Yeah, good point. So we're going to write this all up and submit it as a report. And I think the report can do a number of things. One, it's got to inform John Stein, but even more, I think we can use it as leverage for moving this effort forward.
I would say that a lot of the draft skeleton of the model kind of ways actually get at the first concept of even a budget or a cost that could be involved with those social levels for policy people as something to do now. And then it has to go back to the other groups and it has to come back into the other process. I think if we can set about those really kind of captures it, we can do that to go with our stuff. We need to have that right away. So I'm hoping that we do with some kind of an actual plan.
Okay. All right, well, I'm going to move along to the next speaker. So this first session, we really are trying to get up to speed on sort of what we're talking about here with respect to using indicators and forecasts. And so we have Kit Rawson speaking, we have Mark Scheuerell, we have Pete Lawson, and we have Michael Schmidt. And so with that, I'd like to introduce Kit Rawson. And he is going to be bringing us up to speed about sort of the big issues particularly within Puget Sound.
Where's my pointer? Good morning. Are you going to put my talk up there? So, okay, the only biographical thing you need to know about me is many years ago I went to a school with a lot of really smart people who accomplished a lot of really great things, and I'm just a fisheries guy like the rest of you. However, we have a little email group, and so we had to predict the outcome of this presidential election. And 1 week ago today, I turned in a map that was exactly like the final map, and Florida will be blue on the final map. And they all think I'm really smart because of that. But no, I know about statistics and I know about forecasting because of the work we all do. So I think we do know something, and you'll see some errors here in my talk, but just remember that we really do know a lot. So, and Corey and I didn't coordinate. I'll have all my little jokes about forecasting as well. So I'm not talking about marine indicators at all. The rest of you are going to do that. So I'm going to talk about the species and stocks of salmon we have in the Salish Sea, the management structure. I think any of us who've tried forecasting know some of the hazards, and I hope we know when to break the rules. This photo is of Lummi Nation fishermen in the U.S. part of the Salish Sea catching Canadian fish, Fraser sockeye, so it merges many of the elements that we have together here. Our Salish Sea is map here. We saw a lot of maps of this on Monday and Tuesday. We have 8 million human population. I was lying in bed the other night worried that whether this number was right. I got this from the Sea Dock Society website, and I'm on this was put on when we succeeded in naming this the Salish Sea a little over a year ago. I'm on the board of the Sea Dock Society, and I realized that I said you got to have an accurate number. This number comes from me anyway, and I was sitting there worried about it, but I was the one that gave them that number, so I still don't know if it's right. We have all 5 species of Pacific salmon in the Salish Sea pretty much throughout. That's a pinch we left off, Corey. It's Chinook, coho, chum, sockeye, pink, and steelhead made 6. So, and pretty much throughout the Fraser River, which I've been criticized for this map because it doesn't show the whole Fraser watershed. I can find it. Fraser produces most of the fish, but all our watersheds around here produce all those species of salmon. What do I do? Don't count this time, your Lord. All right, so I was wondering how many fish in the sea, and I got some help from some of you on this. I was sitting in the back row, and then Andy Rankus finally gave me the coho number this morning. Anyway, we do have more fish than people. This would depict a recent average odd number year. If you take the pinks out in an even numbered year, when the pinks don't run, we'd be pretty close to our 8 million people. And when we cycle down, we might be a little bit below. But so far, we are in the more salmon than people stage, which is good. The pink and sockeye numbers here are just for the Fraser River, so we would have a lot more pinks and a few more sockeye around the Salish Sea. So I was just kind of interested in looking at that statistic compared to people. I think it's always good if we have more salmon than people. We have, and this is going to be really important when we think about marine indicators for forecasting, because we have quite a diversity of life history types, both within and between species. And I use the Canadian terminology because I read the Canadian books. We have stream type and ocean type Chinook salmon, both, and I think that diversity is really important for stability of Chinook. They have a significant Salish Sea resident component, variety of ages that returning, and all these things will interact with the marine variables too.
give us the floor. We already see an error, I see there, but I'll just keep plugging along. The coho or arco or mainly stream type, I think we heard some discussion the other day that there might be some more diversity than that. And so I think probably all the species are a little more diverse than this. But the point is that we have this diversity within and among species, and this is how you get at the life cycle and how the different ways that fish go through the life cycle in the Salish Sea interact with the marine indicators that we're going to be talking about. Another thing that's a reality for us here is a very high fraction of our stocks are considered to be depressed or threatened or endangered or critical. I have some statistics here for the U.S. side of the border. I don't have the information for the Canadian side of the border, but we have, so of our 6 species, if we, they're in U.S. Endangered Species Act implementation, they're divided into ESUs or evolutionarily significant units, and half of those are listed under the Endangered Species Act, or Puget coho is of concern. It's not listed, but it's a candidate species or it's species of concern. And then if we look at the population structure and divide them into their individual stock components, just on the U.S. side of the border, 37% are depressed or critical in the state and tribal analysis of the stocks. So when we manage our stocks here, we can show graphs of declines in stocks over time and everything, but pretty much throughout our species and throughout our area, we have a lot of species of concern. We have a huge amount of hatchery production. I have we need some Salish Sea wide maps of all this stuff, and at least I don't have those yet. And if they don't exist, I think we need to produce those. So I got the one on the left from Peter Van Wil's DFO. The blue things are restoration projects, but the green and red are hatchery programs on the Canadian side of the border. That shows more than the Salish Sea, but and the right is Puget Sound, and that shows hatchery programs in different colors indicate whether they're run by state, federal, or tribal managers. So we have hatchery production throughout. It's mainly Chinook and coho. We have chum, sockeye. It's mainly steelhead also. We have steelhead throughout the area. Then when we have fisheries, we divide the area. We have regions of origin. We divide into catch areas. We have every fishery. I'm not going to go through the different kinds of recreational and commercial fisheries that we have, but the point is that we have to manage the mixed stock fisheries pretty much everywhere we fish. We have all of our stocks travel through these areas. We record catch by area, and we have to divide that up into stock by stock impacts in order to figure out if we're meeting our management objectives for each of the stocks we manage for. On the U.S. side of the border, we have 6 regions of origin that we manage for, and those are divided up a little bit into management units with objectives for each management unit that have to be met. Also, on the U.S. side of the border, we have the state of Washington as a fishery manager, and we have 17 sovereign tribal managers of the resource, and we all have to agree on management objectives, resource status, forecast, the things we're talking about today. And now, on the northern side of the border, we down here look up there and go, man, you guys have it great. You just have BFO, and it just must be a piece of cake. You just decide what to do, and you do it. I'm sure it's not that simple, but that's how we think about it. And so, sometimes I have a hard time getting numbers and understanding. There may be some things going on. So, kinds of forecasting I want to talk about really quickly. For many of our species, I'm going to put sockeye pink and some in this category. Yeah, we make preseason forecasts, but really, the fish return to terminal areas, and we do what we call an in-season update, but is really an in-season forecast. A lot like the last-minute election forecast, really. It really is. So, and we have some good stuff. The Fraser River sockeye are done really well. I'm going to just show you a really bad example here, just to show you what can go wrong, and point out that I think this could be fixed with environmental variables, which is why I'm bringing it up. So this is an in-season update for chum salmon in the Snohomish River area a few years ago, and you can see this is a model based on catch per landing, and there's quite a bit of variability, but we have to use it, and we have to come up with an exact number, and what we came up with was about twice the actual run size, close to it, and that was a real screw-up. And you might say, well, look, you've got that variability, just throw a range in there, but the managers won't accept that. I don't have time to show you, but this problem was related to an environmental variable, to stream flow. It was a low flow year that was causing the catches per unit effort to be high, causing the run to be overestimated. And I think it's really important to understand that our in-season updates can be made much better if we consider all the environmental variables available to us. So I hope we do that. For coho and Chinook fisheries in particular, we have a whole different management system. We have fisheries from Alaska to California that catch a mixture of fish based on preseason quotas and preseason exploitation rates that are managed by a plethora of agencies: Pacific Salmon Commission, that northern part, and Pacific. That's okay, leave it there, that's fine. Pacific Fishery Management Council in the southern part. Go ahead. So, this is how we do the second one. I finally boiled it down to its essence. We play this game every year, which is we have information on stock composition, and we have abundance forecast, which is critically topic of this. But in this game we play, those things have to be set before about March, and then we go and we meet, and the only thing we can play with is that box that says fishing plan. And we have to play with that box. It's going to be great when the next generation, our kids' generation, gets into this together. And until we get individual stock impacts all right. Now, in the coho model, we have 123 stocks and 198 fisheries in this model. Can you say over-parameterized? And Chinook, we have 33 stocks and 73 fisheries. So we have a lot of output and some input to go into this. So it's very important, though, to get the forecasting part correct in this game, because how that fishing plan affects the impacts really depends on that. This is the kind of output we got. This is for one stock, just showing all the different impacts and the statement. And if you think about, I don't have an example of this, but if you think about some fishery that has a fixed number of fish, and if you have a whole bunch of, say, over forecast, a whole bunch of phantom paper fish in there, then that fixed fishery is going to catch fish that really aren't there, and you're going to be way off here on your impacts, and your escapement and your exploitation rates are going to suffer. And that's where I'm going to talk about the hazards of forecasting. Now, we think in fisheries that we get a lot of great, but I'm telling you, we don't go to jail, and these guys are still in jail in Italy. And I love this. I got a comment here, and I probably can't read it, but it says, I think these so-called scientists should be punished. They're paid to sit in front of computers and monitors all day, and by God, they better get it right. And some of us have bosses, and I'm not one of these people, but some of us in the room have bosses that demand that we get the forecast within 500 fish or within 200 fish. They think we have that power. So I'm going to show, as some of you know, I've been out of the harvest management world for a while, but the Schmidt forecast is one that I've done. So I'm going to show you my latest screw-up. I have these survival rates I computed for recent years. So I used a model of the number of fish released times survival rate, and I didn't know which one to use, so I used all of them for 4 brood years, chosen at random, and came up with distributions of potential forecasts. And this exercise was for 2012, so on the left there would have been my distribution for 2012, but on the right was how they would have worked for prior years so I could check it. So how well do you think I did? Well, you can just look at the red X's are the actual runs. You can forget about the rest of this stuff. So we had 3 years in a row of over forecast, which is a problem for our FRAM model because you're filling these fixed fisheries with fish that really aren't there. So I realized, I get some respect because I've been around for a while, so I had to realize myself that I screwed up. So we had to make an adjustment, which is how I get to my last points in my talk, which is know when to break the rules. And yes, I'm going to use my hero, Nate Silver here. Nate Mantua, our friend, used to be my hero, but I have a new Nate now. Like I said, he gave me the answer to make all my former classmates impressed with me on my ability to predict the election. And people don't remember this well, but earlier this year during the primaries, he has a model, a very sophisticated election model, and you saw from Correigh that it works really well. In one of the primaries, Republican primaries, his model said, Romney's going to win this primary by 10 points or 15 points. And he wrote an article and said, you know what? My model says Romney's going to win by 10 points. Here's factor 1, 2, and 3. Santorum's going to win this primary. And you know what happened? Santorum won the primary. So he used his gut. We had a president, for anyone from Canada, one president back that used to think with his gut. We still don't know what that means. But he did that, and it worked. And we need to do that too. We did that, or I proposed this, and the rest of my cohorts agreed to address the 2012 Scheuerell Using forecast using our gut. We knew there was some marine survival problem that we weren't accounting for. Unfortunately, now I have to show you how we did. How do you think we did? Schmidt came back generally in Puget Sound. This would have been about right on, or a little bit of an under forecast, except for our Scheuerell run. Something else going on. Unless Diego gave me bad numbers. I don't think I could do that. So, using my gut, using our gut, got us in the right direction, but not perfect. Okay. So, one final really important point that I want to make, and again, I'm going to use my hero, the other Nate, on this one too. Forecast outside the range of previously observed observations. The most significant election result on Tuesday night or Wednesday morning, whatever, was 4 states voted to legalize same-sex marriage. That had gone to the polls 32 times before and failed 32 times. So if you had a frequentist approach to that, you would say, this ain't going to pass, or if it passes one place, it's not going to pass anywhere else. Well, but Nate Silver had a model he published in 2009 that used a couple of variables. I won't go into the details of it, but basically he listed the states in the years when they're going to pass this. So the surprise would have been if those had not passed, because he used a good model to predict what was going to happen, and so it was just no surprise, at least not to me, to anyone. And we know from our first 2 days, and we know from a lot of other things, that we have trends that are, things are changing. We have trends. We're going to see some unprecedented times. So this is a oceanic pH graph for about 25 million years, kind of showing 8 to 8.3 pH, and then showing, that's showing projected, a projected plunge in pH. Okay, and I just, because some people don't believe these projections, I have some real data down below from one of the inlets in South Puget Sound, which basically shows pH declining from 1990 to 2002 from 8.2 to the high 7s. So, this stuff is really happening. So, we need to be able to look at these indicators and project outside the range of what we've observed, but to do it in a way that makes sense. But we can't assume that things are going to stay as they are, or we're really nuts. So, beautiful ecological interaction in the Salish Sea, witnessed by me and photographed by one of my friends, and that Schmidt salmon was as big as the seal, but the seal won that battle, and so so I will share that with you, and hope that we have a good workshop here and come up with a good plan to improve our forecast.
Our next speaker is Michael Schmidt of Lawson Using, and he's going to talk about the sort of what went on with the first couple of days for those of you who weren't here. And at this point, I'd also like to do something which was on my mental list, but it's kind of mental this morning, so I'd like to thank Michael of Lawson Using for partnering with us and for really helping to organize a lot of this workshop. And so thank you, Michael. Thanks for all your time. And also I'd like to thank Laura Blackmore as well. She's been instrumental in a number of different aspects. Thank you. And you will see over the next couple of days she's been very effective. So with that, I'd like to introduce Michael. Thank you.
Thank you, guys. Please bear with me on this one. It's all text. I had to try to summarize 3 days for you guys, and we'll see how it goes. I'm going to be facing that way most of the time reading. All right, so just to give you a little background, for those of you who weren't, see, I can't even work my own. So, just to give you a little background, we have been working with the Pacific Salmon Foundation of Canada for about a year and a half now, and then locally with a technical team in the U.S. To start getting the bones of a research proposal together to identify the primary factors affecting survival of salmon and steelhead in the Salish Sea, with a focus on Chinook coho and steelhead, given their precipitous decline since about the late 80s or so, or mid-80s. And so we decided to basically come together with some of the research work, or planning work that was done on the U.S. side, with work that was already done beginning in 2009 on the Strait of Georgia side, and bring in some other more contemporary information into a workshop that was Monday and Tuesday of this week. It was very much a multidisciplinary workshop because we're starting at the point of saying, well, there's all sorts of things that have changed in the environment. Let's take an ecosystem approach and then whittle down from there. And this is a bit of how we began to whittle down the approach. And so it was 2 days of a group of about 100 and 90. There were about 60 experts and 30 observers, but most everybody there was experts. We went through and folks presented the different factors possibly affecting survival. And then we had discussions with the larger group about ways to move forward, and then met with an advisory panel on Wednesday, yesterday, to further refine that approach on what to do next. So, just like I said, the objective was to determine the critical elements for a joint U.S.-Canada research program, and the sub-objectives, I guess, were determine whether there's sufficient ecological or operational merit to doing a joint program, whether a whole ecosystem study is needed, what factors should be investigated and research components implemented, and what the resulting program should look like structurally and operationally. And again, it's just general recommendations on those, with the idea that we refine it going forward. Next. So for the first one, the question being, is there sufficient ecological or operational merit? The answer was yes for an international program. There is, from an ecological perspective, there are presentations that show that the physical aspects are largely shared. And then, coarsely, if you look at the trends in survival of a lot of the populations, they're also shared. And then, but I guess the finite on that was that the advisory panel suggested that you look again at the ecological information, the operational needs to help inform where and how and to what degree you would collaborate. And then one significant benefit that was identified that is if we are going at it internationally, there's a much greater likelihood that whatever outcomes we find will be accepted by the greater community. Next. Again, sorry, lots and lots of text. So, is the whole ecosystem study warranted? Well, kind of. What the general conclusion was is that you really do need to start with the bottom-up, which you guys are largely talking about today. Food supply likely mediate survival. This is for Schmidt and Coho, as we were discussing. But top-down processes are playing a role. Basically, you need your bookends. So you need to have the bottom-up, and that's going to be your foundation. But because you don't find dead fish around here, it's good to have a predation point as well. And then within that, you can start looking at the other factors that were discussed, such as toxic disease and so on and so on. With steelhead, there was stronger evidence of a non-size selective instantaneous mortality occurring. So first steps really focus around determining whether or not it's a predation effect and whether or not you can implement some sort of experiment or study to start determining whether or not that's occurring. Go ahead. So the priorities that were identified over the workshop and then by the advisory panel was just organize and better analyze existing data, in part to help facilitate a path forward, use targeted analyses to fill high-level information gaps, and you guys are going to talk a lot about that over the next couple days. It really aligns with the monitoring or the ecosystem indicators from forecasting part. The biggest gap was the zooplankton and the entheoplankton piece. Create a standardized monitoring approach. Again, that's something you guys will be talking about. And then develop large-scale and targeted experiments, which is one thing that the Salish Sea folks, the Strait of Georgia folks did touch on a little bit in their research planning. We did less so in ours. So, go ahead. Yeah, again, sorry. Really, really apologize. So organize and better analyze existing data. Really, we're focused on modeling in a suite of models because, as was stated in the first 2 days, one model does nothing. Two models are better. And also, it's because you're looking at bringing in multiple factors, and also as many of you know now about outcome-based management and adaptive management modeling, you have to incorporate that as well. So you're looking at a suite of models to start bringing in early on was the recommendation, earlier than what usually is done. Oftentimes modeling is done after you start getting data in place, but we do have some data, historical data to begin utilizing to help maybe refine a path forward as we were talking about. Evaluate different modeling approaches. As you know, we have the EWE modeling, ecosystem with EcoPath. There was some modeling presented for the Strait of Georgia that Ian Perry has done, and you'll see a little bit of that today. And we can look at simple models to start and then more comprehensive tools to both really enhance our view on what to do, and then also to bring in the data that we collect over this project to again, build a more comprehensive vision of what's going on in the environment. And then one recommendation also is do more precise evaluations of coherence in the ecosystem, which means, really evaluate how tight the connection is between the Strait of Georgia and Salish Sea, both on the ecosystem level and also on the response level, which is the marine survival side. So we have looked roughly at survival trends, but we really haven't done any sort of really strong analyses on them, and they're asking to do that as a starting point. Determine whether ocean survival can be quantified or parsed out from Salish Sea survival. Basically, if we can remove the signal, the ocean noise a little bit, then maybe we'll get a better idea of where in the Salish Sea we're seeing stronger problems, I guess, or lower survival. Make sure models are spatially explicit, use historical data, and look for regime shifts. That seems to be one of the most important benefits of when you have limited historical data, is you can look for bigger flips, and that may tell you something, especially because we seem to have seen something in that late 80s period. And then also evaluate correlations that once worked and now don't, and versus ones that work now. And that's not just here, that's even thinking more broadly about correlations maybe that worked in the Columbia River and that don't. It's just to start getting an idea of maybe how regime shifts are occurring. And then cumulative effects was considered kind of a big hole when you're starting to bring in these factors, and again, modeling would be the way to really get at those. And then the last one was just that we didn't have a big discussion about the size and composition of juvenile salmon, and there is some samples of data out there that probably could be compiled a little better to further elucidate variability. Next. So again, most significant data gap is ichthyoplankton, zooplankton. The data that we do have from Dave Mackus up in the Strait of Georgia is fragmented, quite largely fragmented. He did have some quantified data, but not much, and most of what he did was on the coast. And then from Dan Pantilla from the Department of Fish and Wildlife, he has a large qualitative data set that we are looking to try to help compile, but it's really qualitative, so that's the concern about what that will mean for how useful it will be. So we actually, along with the team, has an assistant who is trying to help with that, and we're looking for funding to really work on that piece. And then there are some other sporadic zooplankton data sets for Puget Sound, but really the Pantella data set was the one that stands out. And really, ichthyoplankton data is just not there. So that's a large gap, and we had a lot of discussion about how to tackle that. Switch, please. So again, standardized monitoring approach. It was emphasized that, and you guys obviously are going down this road. If we can't fund it, at least let's get a standardized approach together, because there are a lot of people working out there, and we can at least start doing things in sync with one another. And it's a great place to start. But we're also optimistic that we can find funding. But the first step is standardize, develop standards and protocols, and also consider how we can do better data sharing across the borders, and obviously on this side. When we're talking about the fundamental monitoring, monitor the bottom-up processes and fish together. Obviously, you guys know that. That's what we're talking about today. Suggestions for bottom-up modeling is to use circulation models to help refine the spatial extent of sampling. This is both for the physical and the fish sampling. Focus on zooplankton and ichthyoplankton, like we talked about. Fish sampling should be done concomitantly at the same time. There was a recommendation to be cost-effective about your physical monitoring. That really it's about the zooplankton and ichthyoplankton, the direct link to the salmon. Again, that's what you guys will be talking about mostly today. And then consider the entire year, not just the spring bloom, because it's not completely apparent that the spring bloom is the fundamental driver here, that there may be more to it. So when you're doing your analysis, just look at the entire year, let the fish tell you when you should be monitoring most intensively, and go from there. There was a lot of discussion about lipid content analyses and the need for that, so that really should be part of whatever program you're putting in place. Pick populations for a case study. You should include those who are doing well versus those who aren't, so you can do the comparative analysis, and that's within and among species. And then you need to understand the condition of the fish entering and possibly leaving the Salish Sea, because we don't know basically where exactly the effect is occurring, and that will help us the fish leaving the sea component is quite difficult, but we do have a handle, especially on the Puget Sound side of the fish entering through a lot of the smolt trap efforts that are going on. And then there was a discussion about some large-scale and targeted experiments, and these are just examples. A lot of talk about hatchery manipulations. There was a lot of that done in the 70s and early 80s. We could bring that back again, but think about it on a larger scale. Look at doing integrated experiments across the border. And obviously, a lot of you know what you could do. You can change species. You can change life history approaches, size, timing, numbers. A lot of things you can do there. Mesocosm studies were brought up using net pens, so you have some control over, you have the fish, basically. You won't lose them. So you can see possibly looking at growth rate restrictions in the marine environment and just other effects. And then targeted acoustic studies to try to identify hotspots. That was really pointed out for steelhead as a starting point. It's kind of been done for steelhead to an extent. Right now, there's a group under Barry Shukian, especially Megan Moore, who's leading it. They're taking all of the acoustic data from Puget Sound for steelhead and trying to refine basically where a lot of the mortality is occurring. And Admiralty Inlet really sticks out. So that's an example of how we could do that and then further build upon that. And then comparative survival studies. For example, this is for steelhead as a starting point, maybe do fish released before the hotspot and after the hotspot to see if there's a survival difference, so you can get at, okay, whether or not there's really something occurring. Next. Operationally, and this is just some general operational recommendations. Continue to work on developing an international management and public engagement strategy. We really want to build upon what's there, obviously not try to reinvent the wheel. And we, the Pacific Salmon Foundation, along with the Kings, will continue to be involved to help coordinate, strategize, fundraise, and all that fun stuff. And then work on international work groups. We should go basically from the way we've been to having separate disciplinary work groups to having more multidisciplinary international work groups. And the structure was basically retrospective and modeling, experimental and monitoring. Those would be the three work groups moving forward. And then develop a fundraising strategy, which is what we are already working on. So, I think that's it.
So we'll move right along, and our next speaker is Mark Scheuerell from the Northwest Fisheries Science Center. We're going to dive now into some of the potential benefits and challenges of forecasting, and he's going to be talking about the benefits.
Is there a pointer here? This doesn't advance at all. That's just the pointer. Good morning, everyone. I have been tasked with discussing the promises of using indicators in forecasts, and so I'm going to rifle through several examples of how my group has essentially done that. None of the examples I have for you today are actually from the Salish Sea, but I still think it's germane and should be of interest. So first, I want to just make a general comment about forecasting before we get into this. I'm from Minnesota originally, Great Midwest, and I'm going to tell you a little story about a rather small river in the Northwest that at one point got very large. And that is that in February of '97, forecasters from the National Weather Service told everybody that they were expecting the largest flood ever recorded for the Red River of the North, and they predicted a crest at Grand Forks of 49 feet. Well, lo and behold, come April, the crest made 54 feet, caused $2 billion in damages to several towns and communities. This is roughly what it looked like. Everybody freaked out. They said, what on earth, you guys got this wrong, it's your fault, just like the meteorologists or the seismologists in Italy, right? You know, they wanted people strung up. The reality is when the forecasters went back and looked at this, they were well within the 10% error on a long-term basis. So they nailed that forecast, essentially. So the bottom line here really is that everyone, be it those of us sitting in the room, the general public, whomever, really needs to understand what is involved with the forecasting, in particular uncertainty in forecasting. We always tend to focus on these point estimates, and we're not really always thinking about this general uncertainty. So, with that, I'm going to talk just briefly about accuracy and precision in forecast. So here is some real data for precipitation this is northern latitude, so here's from 60 degrees north to the pole. This is from the IPCC. And these are various projections of what they think is going to happen in the future. Now, if you were going to try to guess in 2020 what exactly the precipitation anomaly was going to be, you'd never get it right. Look at all this wiggling. It's going up and down, up and down, up and down, and up and down. So the probability of you actually getting it right is relatively low. But as an aggregate, if we thought about perhaps the mean in here, we might get pretty close, and then we would see some uncertainty around that. So accuracy, one problem. Precision is the other problem, the sort of variance around the forecast. So here's now same group, here's temperature in Fahrenheit, here's the historical record, and then these are model projections moving forward. And based on some ensembles, they see there's some mean forecast here, but then there's all this uncertainty around it. And the other important thing is to think about is as these forecasts get farther and farther away from contemporary times, this uncertainty builds and builds and builds, and we have to keep that in mind. So sure, if you can predict the election one day beforehand, okay, that's pretty good. I'll give you some credit. If you had done that 4 years ago, we'd all be a lot more impressed. Okay. So what about forecasting fisheries? Well, this is done all the time. I mean, people don't really think about it as such, but everything, all the stuff that Kit talked about earlier, you're going to try to figure out how many fish are coming back, somebody's doing it. Oftentimes it's done on something simple like spawning biomass or age structure. We use just basically a stock recruit relationship. A Ricker model, a Beverton Holt model is a forecast. You get some estimate of what the spawning biomass is, you have some estimate of what you expect to come back from recruits. More recently, we're seeing now that, obviously, as the topic of this forum, is this inclusion of environmental indicators. So starting to bring in some other things besides just the fish themselves. Maybe it's a little bit more information about those fish, but also something about the environment. Is it physical, biological, chemical, whatever the case may be. And as well as the fact that we're now starting to develop more and more sophisticated mathematics and statistical approaches that actually help us incorporate all this in sort of a meaningful fashion and generate a meaningful forecast. Okay, so first thing I want to talk about here is a sibling regression forecast. This is very commonly done. You count some year class like Jack's in some year, and then based on the total adult return summed up over some years, or perhaps it's just the next year, you see there's some nice positive relationship here. And so we can fit a linear regression line on here, and that looks pretty good, and we've got a mean and some variance around this. It turns out that this is actually a forecast model, though, so we actually need to incorporate some additional variance here. So in any given year, if we counted 1,000 Jacks, our prediction would be 30,000 plus or minus 20,000. Okay, there's your standard sibling model. What typically happens then is we get fixed. Here's our model, it made some projection. Oh, what happened here? I mean, that tends to be, well, depends on who you are. If you're an ecologist, this is okay. If you're a fisherman, you're in sense. But anyway, the point is, this was a real surprise, and we don't know how to treat this. So moving forward, what are we going to do? All right, the other problem we run into is this. These are the data I just showed you. And then we get this sort of thing where all of a sudden we get some number, and Kit mentioned this, well outside the observed range. What are we going to do? This happened in the Columbia a few years ago. Okay, we're going to treat this point in a regression context, so we're going to redo our whole analysis. Got to think about these things. Well, if we think about this in general, okay, so we've got this line and we've got some uncertainty around it. Well, why aren't all of these points lying on this line? What is causing this variability around here? So if we think about that, these deviations of our prediction from our expected, there may be something else out there that can help us inform what causes those deviations. Can we, in fact, build something else into this model that sucks all of these points up toward the line? And that's what I'm going to move into now, sort of using indicators. Well, from a salmon perspective, talking about the environment influencing things like survival is not new. People in this room have been publishing on that for years, decades for that matter. It doesn't matter what it is. Pick your index. PDO, upwelling, elution, put a whole bunch of them in there. We all know now that something out there in the environment is driving survival. Okay, here's an example that I've been using a fair bit. This is an upwelling index at 45 north. Here's from about mid-40s through 2010 for April and for October. And in the California current system, generally what happens is in springtime, winds start blowing from the north, and we get these upwelling events. We have all this strong upwelling. There are times when there's not much upwelling. There's actually times when it's still downwelling during April. It's a relatively delayed upwelling period. And then in the fall, winds switch, and we end up with a general downwelling pattern. Well, now we know from sort of well-defined regime shifts that have been done not just based on upwelling, but lots of other analysis. There's one period here, and another period here. And if you're in our part of the world, in general, fish did really pretty well during this time period and not so well during this time period. And if you just look at these without really thinking too hard, this tends to look like pretty good upwelling, and this tends to be pretty lousy upwelling. So let's try this. Maybe upwelling can in fact tell us something about survival of fish. So a few years ago, I worked with a colleague of mine to generate some data, and I did the modeling, and basically what we're going to ask is what the smolt to adult return rate, so the smolt to adult survival, as a function of upwelling. So we've got basically, this is a linear regression model here, but we're going to make it a little fancier by allowing these parameters on that model to actually change over time. So essentially, I'm fitting a non-linear model using sort of a linear context. But in a regression aspect, all that means is the slope gets to move up and down a little bit with that relationship. Okay, so we use that upwelling index that I just showed you a little while ago, and SAR data for, this is Snake River, spring, summer Chinook. The data are the blue dots here. The black line is my mean forecast, plus or minus 95% credible limits. And in fact, we did really pretty well. Again, these are true forecasts. So this is not take all the data and try to fit this model post-op. So I guessed what this point was going to be before I got there. The model guesses. It actually does pretty well. Okay? In fact, I can explain about 2/3 of the variation in a forecast context using just upwelling. Okay, well, this is just the survival component there, and that's interesting. But if you're in the business of trying to figure out how many fish we're going to be able to catch or how many fish we need to be able to take, that sort of thing, you'd like to have something about actual numbers, not just these survival rates. So if we think about this now in sort of a age-structured population, in some year T, we've got spawning going on, eggs are deposited for a stream-type Chinook. Let's say we've got fry, the smolt. They're going out to the ocean, some are coming back, some are surviving, coming back, this sort of thing. So here's our life cycle. Unfortunately, we typically only get to observe these things. So maybe we have something about this. But in general, we're counting these fish that have now returned. We don't know what's going on out here in the ocean, and in some cases we have. Well, when we do that, we're basically stuck with our sibling model. So we basically use something about age 3s, use a simple model here to predict the number of 4s, use 4s to predict 5, etc. In some cases, however, we actually have smolt data. And in the Columbia here we do, so what we can actually do is incorporate what we're calling a smolt to adult model, and that is if we know something about survival, this SAR that I showed previously, and something about the proportion of propensity to breed, this is sort of a combination of your willingness to come home and age structure, you can actually, based on these smolts, get some additional information about how many of these fish you expect to come back. But if we think about this model just by itself here, and think about these parameters in this model, we need to know something about survival and these age proportions. Well, it turns out that none of these are constant over time, right? We all know that. Survival goes up and down all over the place, and age structure changes a lot. So we essentially need something to help us inform how that's changing. And so this is work now that Eric Scheuerell's been leading, and what we are doing is using these smolt numbers and these counts of adults and our estimates of survival, and we've got basically a log likelihood function here that basically takes something with respect to the environment, and then we're using some autocorrelation to estimate what that survival is. And then we can also build a model here for these age proportions. And we've got one more recently now where we're actually using environmental covariance on age proportions. Okay, so this helps us build this piece here. And then we can build an observation model on top of that using these counts and these estimated proportions to actually make predictions by year of the number of age 3, age 4, age 5, and essentially those size. Okay, well, that's a lot of hocus pocus. Is it worth all the trouble? I mean, a simple linear regression sibling model is pretty easy to do. How about this? Well, we've been testing this again using Snake River, Spring, Summer, Chinook. We've got 45 years of data now, I guess, using counts from Uppermost Dam. And then we can use a whole bunch of covariates. We've got some Columbia River flows, PDO in the spring, some upwelling in spring and fall, like I used years ago in my model, and sea surface temperatures. And we're going to jump right into the results here. So here's, first of all, Eric's done basically a regular old sibling model. And we use some amount of data at the beginning to train this model. We got to start with something. And then as each time step moves along, we can update that regression model. And then we can make a forecast and create some uncertainty around it. So here the black dots are the data. The thick line is the mean forecast, and the thin lines are the uncertainty around it. And, you look at that, you're like, oh, that's not too bad, actually. But I do want to point out that, look, in general, especially in some of these years, the uncertainty around these forecasts. Skip was, this is going to drive someone nuts to tell them, it's orders of magnitude different. Okay, here's our SAR covariate model. Same thing, same data, same lines. In general, looks pretty good. One thing that you should draw your eye to is that these uncertainty bounds are much less than they are here. And we can now formally ask how good are these models doing, and we can do that. There's several metrics that are out there. The one I'm going to use is root mean square error. It basically is expressed in the numbers of fish. And it turns out that the root mean square error for this model is 14.7 thousand. And here's 11. So this model is in fact doing much better at both an accuracy and precision perspective. Okay, now I just want to sort of build on this point a little bit. Let's just look at 1 year here. Here's 2005, in both cases. And we're going to take a slice sort of through the model output right here. And here's our sibling model. So here was the observed. There were about 22,000 fish that year. And here was the point estimate with some uncertainty around it. So in this case, we can actually say there's relatively low bias. The point estimate was pretty close to the observation, but there's pretty high uncertainty. This distribution is quite wide. If we contrast that to our SAR covariate model, again, we've got relatively low bias. In this case, it was an under-prediction, but the distance here is roughly the same as this distance. But look at the uncertainty around that forecast, much, much less. So in fact, we've been able to shrink those sort of confidence intervals down quite a bit. Okay. Then the last thing I want to just talk about is we can sort of say, well, in a context in particular for species that are relatively low abundance, we may not just be interested in trying to get, okay, how many fish can we catch next year, that sort of thing, but we may be asking, what's the probability we're going to fall below 5,000 spawners or something like that. And again, using those exact same models, we can basically create these Q2 plots. And the idea is that if they were perfect forecasts, it would lie right along that line. And our sibling model, in fact, is too optimistic, too many of our forecasts are ending up down here, and I could go back in a moment to see, but basically what happens is you tend to overpredict or underpredict quite a bit. This SAR model here is in fact much better, still not perfect, but again, is doing better than the sibling. So just to sort of wrap this up, basically what we're dealing with here is, sibling models are pretty easy. They do work in a lot of cases, but there's no reason now, for a variety of reasons, that we shouldn't be pulling in these sort of environmental indicators and using perhaps more sophisticated mathematical models on top of that. With that, I thank you.
Our last speaker for this session is Pete Lawson, and he will talk about perhaps some of the challenges of using indicators.
Well, I find myself at quite a disadvantage here because I'm speaking last in the session, and everybody who's gone before me has basically talked about some of the things I had to talk about better than I have. But the first part is I'm going to show you is just some ideas that I've about what makes a good forecast and what makes a good indicator that I've just jotted down. Was sitting here in the past several days. So there's nothing here that you don't know. This is kind of like the driver safety training that you all have to take every 3 years, whether you want to or not. They remind you to look in your rearview window or your rearview mirror and leave a safe following distance. So just treat this as sort of a refresher course. Don't use the mouse. And does this have a laser on it? The orange button is the laser. Okay. Well, I've watched many people have train wrecks with these controls. So here we are. What makes see, I've already. So what makes a good predictor? One thing is it needs to capture the broad patterns of fluctuation that you see in your population. Some things can capture an average trend, but don't capture a variation. And Kit talked about the second point, does it have sufficient accuracy for use in management? Mark talked about this too. You can have a predictor that has a high R-square, but when it misses, the managers don't like it, and I'll point that out again later. A couple of another practical use, you can have a predictor that works really well, but you can't get the data for it until after the season starts. So you really have to think about choose your predictors based on the availability of your predicted variables. And then finally, and Mark talked about this really well, to express your variance, your uncertainty explicitly. Now that doesn't make anybody any happier, but at least maybe it'll reduce the chances of you going to jail. I don't know. So then from there we want to look at what makes a good indicator. And the indicators are of course the independent variables in your model. So first, and this is sort of like it should have a quantitative relationship to what you're trying to predict. And not only that, you should be able to explain why it might have this relationship. There was a period of time when the Dow Jones Industrial Average, as it was climbing, would make it a very good predictor for salmon, coho salmon, as they were declining. But there was no real obvious linking mechanism. So I rejected that as an alternative. Estimated or measured with precision, and that precision is known. One thing that's a warning sign when you build your model is if the model predicts your stock with more precision than the variables are measured. So there are several temperature regressions with Oregon Coast Coho that had like 90% R squares. And we know we weren't measuring a statement with 90% probability. So that it feels good, but that's a caution. It's really nice to have long, consistent, dependable time series that you're sure are going to continue into the future, and that's really what we're here talking about today. And 40 years is not too much. And that's another problem when you say, okay, well, we really need to know plankton in Puget Sound, and we start measuring it next year. It's not going to do us any good at all for a decade. So if you want to solve the problem now, it's a different question from if you want to solve the problem for the next generation of fishery biologists. And we probably want to do both. That's something to consider. Your indicators, to me, the later in the life cycle your indicator interacts with your stock, the better. You can predict a number of eggs or egg survival with confidence, perhaps. But there's so many things that happen between the time that egg survives and the time it comes back as an adult that it doesn't make it very good, or you don't have a lot of confidence in the predictor. And that's what Mark was talking about, bringing in other variables that incorporate the later stages of survival. So, again, my main frame of reference, I know nothing about Puget Sound, is OPI area, Oregon Coast, and Columbia River Coho salmon, and Chinook salmon. The coho, there's a jack regression with adults, a sibling regression. If you know jacks, it's a lot better than if you know smolts, and that's better if you know spawners. Think of any spawner recruit relationship you've ever thought of, and it's like a shotgun blast. Because maybe, we know there's some relationship between the number of spawners and the number of recruits, but there's so many other things that play in there that it really, from a management point of view, isn't very useful. And then finally, so to solve that problem, you want to integrate multiple factors and effects. Actually, what I'm saying here is an advantage of JAX, or sibling regression that I've described, is that the later in the life cycle you are, it integrates whatever has happened to that fish beforehand. So you can start with spawners and guess what has happened, or you can look at JAX and say, well, this is the actual outcome. With some certainty, of course, there's always the changing maturation rates, jacking rates, and stuff like that. So Mark went into sibling regressions in a lot of detail, but this is about 40 years of Columbia River jack to adult, and from a a biological point of view, that's a very strong relationship. The R squared is greater than 0.9. And it's explaining the big years as well as the small years, but it's also, that's not the laser. So there we go, that's the laser. So, that year was an El Nino year. That was the 1983 El Nino. That's 1983 El Nino. And we had never seen an El Nino have an effect like that. So we had no way to predict it. It was outside our experience, even if we, so it was just besides the jacks. It's not outside the range of our predictor, it's outside the range of our experience. Then there's another year, 1986, which came in way above the forecast. And I don't think we have a good explanation even now why that happened. Maybe it was a rebound from 1983. But how the heck? Figure that out. So you have some, what other indicator variable are you going to bring in to do that? It's just, it's just not there. So even if you have a really good model, there's going to be surprises. I'm going to talk, we've seen Mark's models, and we've seen Correigh bring up a number of different kinds of models. I'm going to use this exercise that David Roop did with a little bit of help from his friends on Oregon coast coho salmon, which should be a relatively simple forecasting exercise. And one reason I'm using this example is because it illustrates some of the points I've talked about and some others. So to do this, OC and coho have not been forecast well, and that's my fault because I was in charge. So we finally got a bright young postdoc to really bear down on the problem, and he took some of our ideas and extended them and did a really good job. So what we started out with was a list of all the variables that we thought might come to bear, might be important. And not only did we list these variables, we had a hypothesis for what the link between the variable and the cohort was. So these are all environmental variables. PDO, NPGO, we've heard about them earlier this week. Multivariate ENSO index, the ocean Nino index, sea surface temperature, sea surface height, upwelling, North Pacific index, the date of the spring transition. Several of these are known in the past, have been used in forecasts. Spring transition was in the Lagerwell model. Upwelling, Tom Nicholson worked with that. Sea surface temperature was in many of my forecasts. But anyway, we started with a list, and importantly, the Dow Jones is not in here. Dave did a lot of exploration around this list. He not only, and a lot of it was really looking for empirical matches. So he looked at different time periods, usually slicing things up into 3 months. For example, if I can avoid the power button, May, June, July for the PDO. And that is stock dependent. The time, we got to match up the time scale for your stock. So here's a correlation between PDO and there are time series showing the relationship between PDO and the recruits, ocean recruits of OCN. And yeah, it looks pretty good, but there's problems here. There's a lot of variation, and it looks like, especially in the recent times, that the PDO goes up 2 or 3 years before the fish respond. And it goes down, and it takes the fish a while to respond. So we started looking at time frames and treating the PDO in different, we took a variety of long-term averages, or moving averages, and settled on a 4-year moving average for the PDO. And here, the hypothesis is that the PDO, which is just temperature in the North Pacific, takes a while. When it changes on a decadal scale, the biology takes a while to respond. So if you look at this, it matches, especially in this recent time period. It matches our observations a lot better. So we take that as the basis for our forecast. And then there's a lot of more variation. So we try to explain the residual variation outside the PDO. And those other variables came in to do that. But what we found was that there were a lot of different models that did a pretty good job of explaining it. And these are all PDO 4-year averages, plus 2 other predictor variables in different time periods. And our squares are all very close in each of these models. OCV is like a jackknife where you take one out and fit the rest of the model. And HSS is timecasting, where you use the model data to date to forecast the next year and then update the model. So, interestingly, if you look at R squared, it's about 0.7, 0.8. If you take the mean of all the models, you get an R squared of 0.81. So by considering all the models together, you've done 2 things. One is you've actually improved reduced your confidence limits, and you've also armored yourself against the risk of one or another of these models failing. So if all of a sudden the ENSO index does something really weird, it won't be the driver of the whole forecast. So here's how the model fits, and it actually fits quite well. The open circles and the black line are the observations, and each of the colored lines is one of the different models. They all are tied together by the PDO, so they're going to be close, but they actually follow the time series much better than earlier models had. Then if we do the hindcasting, or so starting with 1990, using this period to train the model and then going forward, you can see that it doesn't fit as well, and it tends to over-predict here and maybe under-predict here. But it's driven by 2 things. One is this long-term decline in the 70s through the 90s, even as far as 94. And the other thing that drives it, and that the model fits really well, is this big fluctuation right here. So I like that because it's capturing 2 different kinds of variation, and it's capturing especially well the recent variation. So that gives me some confidence. Now, okay, this model works now, but how long will it continue to work into the future? And this is just, based on our models have to be based on the past, because we can't predict the future very well. And Tom Wainwright did an interesting exercise where he took some aspect of OPI Toho, I'm not exactly sure which one, and did a 5-year moving correlation. So here we, power button again. And these are a lot of indicators that Bill Peterson will be talking about. PDO up here, PDO and O&I, copepod, H, JAX. But what you see is that here's spring transition. That's one of the really good ones. It comes and goes as a predictor. Sometimes it's really good, sometimes it's not so good. And if you do it this way and look at the PDO for May in a single year, some years it has a positive relationship, other years it has a negative relationship. That doesn't make for a very good predictor. But the main lesson is that here's upwelling. It was really good in the 70s, but sort of disappeared later on. So your indexes aren't going to last that long. That's something to watch out for. And the multiple model approach will help with that. Then finally, the system is changing. There's no doubt about it. We've seen it from the pH swings. Who talked about pH swings? Kit must have talked about pH swings. And we all know from the past 3 days that kelp are gone, helicon are gone, in some places, everything has changed. So we're not in a stable situation. And what Buzz Collins talked about was the warning signs when variability starts to go up. And this is a just very general indication from, this is just based on catch, Alaska to California. Look at the variability in catch in the system. It has gone from being fairly stable over decades to all of a sudden, bam. So we might be wanting to watch out for what's coming next. And I guess I'd say that's our challenge. Okay, thanks.
Oh, we're done.
Do we have all the speakers up here? So we're now having a discussion section. And so presumably you saved up tons of questions, and now here's your chance to ask them.
All right, so I'm sorry, this is only computer difficulty. So my name is Laura Blackmore. I'll be your facilitator. And those of you who have been here for the past 2 days are already doing this, but you'll notice that you'll have a name in front of you, hopefully. What I would like you to do, if you would like to speak to Rebecca's modeling this behavior already, you can put your stand your name tag up on end, and that will help me know that you would like to speak, and you don't have to keep your hand up for 20 minutes, and this is going to get to you. Occasionally, I will repeat the list of people that I have waiting to speak if I have not read your name and you would like to say something, be energetic about getting my attention. Okay. So I have Rebecca and Nate and Richard. Am I missing anyone already? And Mark and Mike. So, and we do need to use the mic because this room is kind of dead. You necessarily have to use fishes in some form when we're modeling. Having cheated down, our self-assessment is incomplete or not very good. Maybe earlier years' historical data isn't very good on self-assessment. Your model shows that you have really good correlation here more recently. So how do we know that our models really aren't working and are working in the face of bad self-assessment data? How do we deal with that kind of information?
Okay, while the mic comes to the line. Is it there? Yes. It is? Okay, I can't hear it. Okay, you can hear me. You don't have to speak. So, Well, if you don't know, if you don't have any confidence in your dependent variable and what you're modeling, then you can't have any confidence in your forecast. So, but yes, that's a problem, and maybe what you need to do is improve your stock assessments before you can try to do a good job of forecasting.
But you need to be using some long-term data to deal with, go ahead and model it. You need to throw out some of the historical data if you know that it's works. So don't be using the long-range data.
Well, if your early data is no good, then sometimes you have to look at the difference between the long-term variability in trends and the short-term variability. So, for example, the early OCN data isn't nearly as good as the most recent stuff, but it does show a long-term declining trend. So the fact that we don't model the interannual variation as well in the early part doesn't bother me so much because of the later part. So, but on the other hand, if it's just noise, then it's not viable.
The other part of that is
the other thing is that with respect to the sort of new and improved math that I was talking about, the way we can address those situations is we have sort of a hierarchical model with sort of two major components. One is the process, the stuff that sort of Pete's talking about, the idea that small fish eat zooplankton and they try not to be eaten by bigger fish. So you've got something you're trying to explain what's going on, and then you have a separate model over here that's an actual observation model. So model A is trying to determine the truth, but we never see the truth, ever. I don't think anybody even here would argue you can't. So the idea is that you've got a second model component that's trying to estimate your uncertainty and actually your data. And it's not that difficult actually anymore to be able to address those types of things. So if you have reason to believe that you don't have a lot of certainty and information that you maybe had 10 years ago, 20 years ago, last year, you can still, there are ways to deal with that sort of mathematics.
Wow, mathematical magic.
I think my question, primarily for Mark, but I think also for Pete, and it's about having a model that evolves. So you have coefficients in your models that actually evolve with time. And some people might look at that and say, wow, that seems really problematic. How can you have a model that is evolving with time because you just have short chunks of data that are going to influence it then? I would guess. I mean, the weight must be weighted towards the most recent observations. Yet, I'd just like to hear more thoughts about why things are good things. There's probably a lot of reasons why it might be interesting. The changes in correlations that Pete showed from the Correigh Greene example.
Basically the way we deal with that is, again, that process component. You have to fit that variance at something, or set some essentially upper threshold. Because the types of models I'm dealing with, if you allow enough variation in the parameters, then you'll fit anything, right? Because the thing can swing all the, when you add an regression line where the line is going to swing anyway, then you're going to nail it all over the place. But that's going to cost again of precision because your estimate around it is not. So as you constrain the ability for that regression to just drop a little bit perhaps, then the bounds will have to go down. This is the types of models that we're using here, most of them now are coming out of the finance world, and they deal with this all the time. So the idea is that human behaviors change, wars start, oil becomes scarce, these sorts of things, so they have to allow for these changes with the understanding that you can't just let things go good and ill. You have to, there has to be some sort of operator there actually points that to some extent. sort of a different thing. I mean, yeah, you can't just blindly go about this. You have to have things back.
I've got a question maybe mostly for Pete. On one of your last slides, you had all the various parameters. It was sort of, it was top down or bottom up, but they had in the middle around the zooplankton, and you had all those red and blue dots that sort of indicated which parameters were important, and none of the zooplankton parameters seemed to have any blue or red. Was that because there was very little data, or because your zooplankton data just doesn't seem to drive your model? Because a lot of the things that are coming out of the first couple of days is that's an area that we don't have good data in. And I just wanted, you know the figure I'm talking about? Okay.
Yeah, the zooplankton data are definitely shorter time series.
Yeah, no one. That middle band there is empty. Is that the zooplankton band?
Copepods biodiversity, northern copepods. And so the zooplankton data basically starts in the aggregate.
Yeah, I've got Mark and then Mike and then Alan. Am I missing anyone?
This one is for Mark. I have two questions, and I can only remember one now. In the analysis that you presented, and I presume this is what presented yesterday when I was in Portland, you showed a reduction in the original mean squared error by using the dynamic model. To what extent this is due to the fact that you're adding more parameters in the model, or in other words, like I suspect it's done the AIC to verify the model performance, and it's actually doing that improve the performance rather than just adding extra noise to this. Because when you add random variables in, you can increase your R squared and reduce your mean squared error. And I remember the other point. And this goes with what Pete was saying earlier, that in the models, when people are trying to build these models, they need to try to incorporate models that have some sort of a link that you can think of in terms of potential mechanisms. And there's sometimes some issues about the objective of predicting and making a forecast versus understanding what's going on. And some of the variables that are coming into your model, like the upwelling in October, worse for predicting, but for understanding is probably useless because the fish that you're dealing with are not even there at that time of the year. So I'd like to have a comment on the first point and then the second point.
Okay, so the first one, the root mean square error is building in the additional uncertainty as well. Right, so every time you add a parameter, each one of those parameters is known with error. So as you say, I can add shoe size or something like that into the model, and I will get a better R squared, but at the cost of decreased precision. And so that's what Pete was getting at. You have within any given model uncertainty surrounding parameters and estimates, but you also have uncertainty in the model itself. So by doing some sort of ensemble model of averaging, then you're starting to guard yourself against the fact that, another year's data means that what was the best model just fell to number 5, and then the others just moved up or something like that. So that's basically what balance is. My rationale for the sort of October aspect was just an indication of sort of the transition to fall, and it's the proximate cause of production or death is certainly not upwelling or PDO or something like that, right? It's just it's an indicator of teleconnection, something like that. So, no, I mean, your point is, well, Scheuerell, what the hell does downwelling in October have to do with the survival of these fish that, as you say, are north of Vancouver Island? I have to just pop out and say, well, it's telling us something about the ocean where we're not actually measured.
So one of the factors that's been a really pretty good predictor for ocean coho is January sea surface temperature in the January before they get in the ocean. So even though so what that points out is that there's time lag in response. And yes, you want your indicators to have a mechanistic connection with what you're forecasting, but at the same time, you have to take into account the time lag in response of the system. So something that's measured prior can very easily be construed to be affecting what happens later. And the same thing with 4-year average PDO. The recent history of the PDO is more important than the current state of the PDO.
This probably goes to all of you guys, but in several of the presentations, including this current discussion, the necessity of having a long-term data set, and especially for forecasting, is obvious. But and so in a way, until we get that, it almost sounds discouraging to start going, say, those ones in data set for Puget Sound. But I was thinking in this all came up how it fits in with the research plan, because there they talked about a substituting space for time approach, and these different sub-regional sampling that would go on. And it occurred to me that it's going to help if we start to see, if we have that data set, first of all, already, we might understand some of the changes that are currently going on. And if we expect climate change to continue to make large, unpredictable changes in the future, just to have that data set built in the future seems important to be able to explain that. Otherwise, it almost, if someone who doesn't necessarily see the utility in funding an effort like this, would maybe see the value of that, not only for the future, but to explain now when you see maybe right away large differences in survival that are correlated immediately with variables that we have no statistical confidence in with a very small data set. But they might point to spatial or temporal differences, or I'm thinking of some of this idea of Beauchamp, but even like food web further investigations that could come out of that. And so I guess I'm saying that there's other utilities that go into the future as well as the current research and understanding this, besides just forecasting, that make it important for us to develop what might not be a useful forecasting data set for a long time, and we can comment on that.
I'll start that one just to say that is it working?
Right. Oh yeah, there you go.
What am I going to do? First of all, if I had just started collecting, say, 2 or 3 of those things, I thought it was too late to start collecting 26 years ago when I started at Scheuerell. That would have been great. So some of us, Pete and I anyway, could say that we can speak from experience, right, and stuff we should have done. I think the relationships are changing, and that was one of my key messages. So the research and the indicators are very closely tied together, as you say. And Mark obviously does have some mathematical magic for dealing with that, but that is the reality. So we have to understand this thing, and again, the monitoring, anything we start now, I think will be really useful for us, and we'll have multi-purposes. So I would encourage us to think about what's best to do now. The other thing is Rebecca's point, and what I got out of Pete's talk too, is that my simple distillation of that is that your precision of your forecast is
going to be at most as good as the precision of your monitoring of your dependent variables. So that's probably a very important thing to get your stock assessment good enough so that you can use that for forecast. Because if your precision of your forecast is better than your precision of your monitoring of your dependent variables, then you probably have a problem. That's what I got. So that's very important to work on that too.
I would just second this comment that there's just no substitution for data. And it doesn't have to be on some indicator that we do or do not pick out in the next 48 hours. But something like smolt count, better water, I mean, just some of the basic biology and some of these things. And yeah, you know, like these guys are saying, where, oh, I don't know if we can make this happen. The next thing you know, we're here 10 years from now. 10 years ago, we really had a good idea. We should have done that. And it's like, again, I'll go back to the finance example. If banks only counted their money one day out of the month, and that month or that day changed from year to year, month to month, it'd be horrible at what to do. They never figure out what to do. But the fact is, they count it by the minute. With really good accuracy. They know exactly where that money is and how much they have. You know, because they know how to steal money. There are some reasons that some fields can do this much better than others. Because, again, he has formed the basis for it. There's just no substitution for it.
Yeah, maybe I can kick in here and draw on the experience of the panel. I'm not too familiar with everything that's going on the coast, but a lot of work in terms of sample stations, and your variables you seem to pick a certain location. I guess the question I've got is, from your experience, can you identify a strategy to zero in on the most important things to measure in the various locations within Puget Sound? Because maybe Whidbey Basin has some different parameters that are important than Bellingham Bay or South Sound. So maybe something associated with the experience you went through and sifting through a wide range of parameters to come up with those that work, that we could short-circuit that process into something much more efficient.
I think there's differences between the California fish and the Puget Sound ecosystem, which really sort of highlights the issue you're talking about. But that we do have substantial differences among oceanographic bases, and for that matter, some of the watersheds that feed into the oceanographic basin. And if you want sort of a starting point, I think we have to sort of wait and listen to some of the other speakers who will talk about that. Certainly we have some information from 6 years to longer-term data sets through the Department of Ecology and others that highlight some of the general differences between, say, Whidbey Basin, South Sound, and Central Basin. And I think combing through those sorts of information gives us a good historical perspective, and as we move forward, we have more recent data sets collected in conjunction with fish, which will make sort of causal connection issue.
Sure. I'm Bill Peterson with the Gathered with all the coal plants and stuff, and I want to make a statement that's been said before by you guys, and that is, if you don't start your time series today, you won't have one tomorrow. Okay? So you got to begin this thing. And once you start, you can't stop. And it's a lot of work. I can tell you a lot of stories about that. But, question for Pete. I read your last slide. That was really interesting. So, has the variance continued to increase since 2001? Your time series talked about 11 years ago. Have you been able to look at the recent data, or is it available enough to know if the variance is still going wacky?
Well, I have not analyzed the whole landscape of California catch time series since then. That was a non-trivial exercise.
Well, it's a really interesting thing you showed there.
But so that you can certainly pick out some stocks where the variance has continued to be really high. Other stocks, it goes down. Sometimes when the stock collapses and flatlines, the variance goes down, but that's not a good sign either. So I think I think that yes, variance is continuing to be high, and I do plan to take a look at it between now and the IPC meeting in October, which is the topic of which is variance.
I think it's really important that variance is actually an inherent part of some of the stocks that we need. I mean, that's the whole point of sort of the portfolio and biocomplexity issue. That if you look at actually variance of Bristol-based sockeye over time, Daniel Schindler will show a slide in some of his talks. It's all over the place. I mean, it says, kind of the thought experience. If you were a fisherman, would you want to fish here? And most people are like, no way. Because you can't, each one of those districts is running around all independent of one another. It just looks horrible. But as an aggregate, it's highly sustainable. And then as Pete was getting at, I've actually been working now with Yukon and statewide Chinook in Alaska because they're under a disaster situation. And in recent years, in the last 10 years, most of the statewide indicator stocks, we've got about 15 now, have become way more synchronous. They're all variances, they're going up and down together, and now unfortunately they're going down. So that variance has actually gone down, which is also a problem as well. So yes, changes in variance are a leading indicator of regime shift, so to speak, but we have to sort of keep in mind what the sort of relative levels are.
I'm running 30 years. Go ahead, Pete.
I was just going to say that life history variability and the variance inherent in that may be different from the kind of variance that's being driven by environmental factors and other things. So there's two different sources of the variability we have to watch out for.
Okay, so I've waited 30 years to get where we are now. I've been a long advocate ever since Percy proposed that we need to look at environmental variables as related to salmon forecasting, and we're almost there. So, my question is, Pete, Bill Peterson, and Mark, what happened? We now have you guys forecasting, we're using environmental data the way I want you to, and want you to. What happened on the Columbia River? 422,000 spring Chinook were forecasted in. I think we got a quarter. Did they not use their models? What happened?
I think we need to have a judicial inquiry on that.
All right.
That model that I presented, stuff that Eric's been working on, and no, they're not using that. And I don't know that he's done his model again. I'll just back up. His model is working specifically on the spring summer Snake River ESP. So that's not an aggregate return to bottom, that sort of thing. I think later, Kurt, maybe he's going to talk about Brian's model, you or Bill, someone who's that. Anyway, another guy in my group is working on that sort of at that large level using a bunch of Bill's data, as well as other people from the region that goes into sort of red light, green light, stop light thing to actually put sort of a quantitative number on that. And his forecast model actually does really pretty well. I mean, remarkably so.
So we're just not applying it in fisheries management, quite yet.
There's some of that, yeah. I mean, there's definitely, I've been in a number of discussions where people think that I don't like that, it's too complicated. I don't understand the model that my financial advisor uses, but you know what? He's doing a pretty good job.
I forecast about 100 million flies, 100 million
My forecast was about on the money this year. But yeah, and just remember that first forecast was a million fish. Remember that? Yeah, and then it came to 600,000 and it dropped down to 500 million, and then I'm looking about for it began with a million. That was the first number this year, and we were seeing more like 200. So, based on yours, fish saw 2 years before the Olympics.
And you see, you really went to see.
So what do we have to do collectively as a group to get you guys moved over into the fisheries management?
I'm not a manager, and I don't want to be a manager. That's the problem. And that's kind of the problem. But we got to meet with these guys and sit with them and talk. They're not going to resume doing business. They're going to work fine. And why should they stop what they're doing and take nice from it? And that's what's so sick. It works most of the time, so what's the big deal? But no, we have to share with these people and spend time with them. And that's what we need to do. And we need to pull it off. And so, do you want to say some words about that? I think that's talking about. So just a couple of comments on that. As I understand it, the tax forecast is primarily based on jack returns, and as Brian Beckman will say, the assumption there is that jacking rate is constant or some percentage, and that looks to have deteriorated. So their forecast sort of has fallen apart in what, Brian, the last 3, 4, 5 years. So as Bill said, we've sort of been working with our thing, and I don't know if it's a competition, but sort of trying to take a bunch of ecosystem eggheads and have them talk to harvest managers is a real challenge. And I think actually we're getting pretty close to that process. I think really starting to happen, but. We sort of built our models in a certain way, and the thing I think is not to make it, like I said, a competition, but here's how we're doing it. This is what we're learning. We'd like to share it, and this sort of workshop is really good. For me, it would be really good to have the same sort of workshop, only with sort of a harvest management context in it, and I think that's sort of the next step is sort of taking the science into the sort of management arena, because I think we know enough now to really start helping with the forecasting in like the Columbia River.
Just a quick comment on that. We just hired him to build egghead into harvest management, so we'll start communicating.
Great. Okay, I've got Lori and Rusty.
Well, I just wanted to second what Kurt just said, and the more that to use the stereotypes, the eggheads work with the managers, work with the fishermen, and actually collaborate all along the way rather than just come together for a 2-day workshop every now and then. But if you can get the managers to tell you what you want, and show them what you've got, and somehow develop an ongoing relationship, it really helps to get the science into the management.
Sorry, Lauren.
In as much as we can emphasize to the managers that here's one model that's done one very good job, and here's one model that's not done a good job. True. Having these model concepts, that's going to be healthy for the forecasting.
I just have a comment that I think part of the reason for this meeting is that the Puget Sound forecasts aren't working like they used to, and it's not. You guys aren't the only ones that have a problem with that in Columbia, and it turns out in Sacramento that Jack relationships are going to hell as well. So you're not alone, and I think learning from each other, kind of what we're doing a little bit here in the Columbia, that they're having the same issues in the Sacramento, what's going on, and so I think cooperating among regions is really helpful as well. So more minds working on the same problem is better than the less.
And Rusty, and then Sue, want to come in?
Just a couple of comments. I think Lori touched on it and covered it well, that using more than one model is a good way to try to get around some of that uncertainty when you model starts not to show up. And certainly then for the sibling models, and this happened in the state of Georgia too, when you have the regime flip or regime shift,
those different models kind of assume that you're having a kind of constant environmental background, and of course that's what happens, is they no longer have a relationship between one year and the next, because it can be quite an extreme shift in the environmental variables. So using more than one model sometimes will get around that issue.
And maybe that's what we're seeing now, is that a lot of variability, as Pete showed, in 2001, which was the year where we had a big El Nino and then a big La Nina and another El Nino. I mean, there's a lot of variability that goes on that can disrupt those models.
I really enjoyed Mark's presentation on describing uncertainty in forecasts. And I think some of the earlier presentations talked a bit about how management doesn't want probability estimations, they just want just single point estimates. So it's more a comment on, from a science perspective, communicating uncertainty in a forecast is very important, and we have to keep feeding it to managers until they digest it. But maybe it's a question on what we are doing and how management is. It's kind of a really general question, and more of a comment on the importance of communicating uncertainty and being transparent about, we're never going to, if we give a deterministic point estimate, we're never going to hit that. That will never be our true return. But if we have a distribution around our forecast, from a science perspective, it's being more transparent, and it's also being more honest, and also more fair to us as science advisors, so that we aren't being held to task when it doesn't come in right at that point estimate. So I just think that's an important message coming out of the presentation, is the importance of communicating uncertainty in the forecast, and keep feeding it to managers so that they at some point digest it.
I agree. It's very hard to talk about uncertainty and probability. That if you were following all this election brouhaha, that was a big part of it. People who know about probability were trying to explain that, and a lot of really smart pundits out there just didn't get it. I think we have to do that with our managers, though. I think we have to take on that hard task, given the intrinsic variability of salmon, and given the uncertainty of our data, and given the fact that a lot of us, or a lot of you who do this, know how to deal with it. So our challenge is to communicate that. Another thing that we've tried over the years that I've been doing this somewhat successfully, somewhat unsuccessfully, is to have management systems that are resilient to uncertainty. And sometimes that works, and you should look at that too, because it's there.
Yeah, I've been trying to figure out for longer than I want to tell you how to come up with a management system that actually can incorporate that uncertainty. The way the management system works is just the point estimate. That's what the specific fisheries management council is doing, and the Magnuson Act is mandating is to manage, be proportionate. So you look at the uncertainty and then you manage for a low ball estimate. The way Kit attempted to do in this great example.
So I've got Terry and then Alan and then Mara and then Nate, and we have about 4 minutes.
I'm just going to speak as one manager. But I know that a few years ago we were looking at the data systems that we were using for our modeling and our predictions. We're seeing that some of the information we're receiving wasn't as stable as it used to be. I'm not explaining data framing or unraveling. And what I was talking to Ken about, if we could use some of the environmental information, is that a way to look at where the models are currently changing and do an overlap of habitat indicators? Will that tell us that we went after a small grant to the Northwest Street Commission to get a small amount of data to give to the Salmon Commission to take a look at that? And unfortunately, I haven't tracked the results of where that's headed, but maybe Kit we're looking forward to. Have we learned anything out of that helps in this discussion, looking at combining the two or doing overlays in a way that helps us with the production?
You should have prepared me for that question, Terry. We'll have to look into that and see what results we have. I'm not sure I can bring that to mind right now. I think we'll have a lot here in these 2 days, though, that will help us do that.
Yeah, I guess I would just offer a comment with respect to maybe a separation between managers and scientists. My experience was with a manager who used to invite all these biologists in, talk to them for a while, and the biologist would never come to a fixed point as to what he thought was true, because it would always be covered by variances. But by talking to a number of different people, this guy would just get a gut feeling as to where the biologist would land if they were not scientists. And he was usually quite right. So you got to have, it's more like having more models available to look at and pick the one that feels it. But maybe folks have some comment on that.
Well, my comment is that's a great way to manage, but I'll just say again, when those conversations happen, I believe that one of the things that we technical people have to communicate is uncertainty and what it means to the manager. That's part of what we have to communicate.
I think this is a really important lesson. People don't like to think about variance. I don't think we're really well structured for it to have essential. And so as much as sort of we can improve that conversation to whoever we talk to with respect to standard management, I emphasize that every time someone comes up with a forecast, there's certainty that would be stuff for us.
So to kind of build on this conversation of variance and uncertainty and handling that and point estimates for the purposes of management, I think that as scientists we can calculate uncertainty and we can calculate uncertainty and still hand a point estimate for the purpose of fishery management. And the way to do this is to have a conversation and guidance policy end as to how much risk within a fishery we're willing to take. So when we have a point estimate that's this is the most likely forecast of what's going to return, there's all these other numbers that are also likely to not quite as likely. And if there's a high concerns or conservation concerns like that, maybe at a policy level, fish managers aren't willing to take that much risk at a higher forecast and want to downgrade the forecast. Or vice versa, if there's on the other end. So I do think that we can calculate and should calculate uncertainty and still hand back a point estimate for the purpose. You have to plan a fishery based on a number of things, and that's one option of an approach.
Right. That's exactly the approach the Pacific Council takes. The groundfish, they have a statistic called P-SPAR, which is an integrated measure of uncertainty, and depending on P-SPAR, it tells the council how far below the point estimate they need to go for their harvest. So, another point to make in interaction between scientists and managers is the scientist's responsibility is to come up with the estimates and the description of the variance. It's the managers and the policymakers whose responsibility it is to decide how much risk to take. So it's really tempting to say, hey, here's what we think is the answer, but you should really be down here because we're sure about that. And another one is to say, hey, here's what we think about is the answer, and here's the how certain we are in that. You decide how scared you should be.
Okay, well, this could be a whole 2-day workshop on uncertainty, but I just want to say that we're all conservationists as well as biologists and managers here, so the precautionary approach to uncertainty is something that we promote a lot, and it has its use. But when we're putting numbers in these models, like FRAM, you have to be careful about that. And one of the problems we have with running FRAM right now is we're all very precautionary, and there's a lot of study. A weather forecasters, but it's 20% chance of rain. You hear that. It's about 5% or less chance of rain. Because you get mad when it rains, you're happy if it doesn't rain. This is what they do. We do that with fisheries too, and it has its place, but it's better to really understand probability and uncertainty and not just be precautionary. So I'm cautioning you about that.
Right, and the other thing that happens here is the biologists are precautionary, and then the managers are precautionary, and you end up with double accounting essentially.
Yeah.
So we have to, as biologists advising the managers, we have to avoid the temptation to insert precaution into our estimate.
Okay. Thanks. So Nate is our last question or comment, and then we will take a 15-minute break. This is a great conversation. I'm sorry to that.
Yeah, I can't help but make the comment that there are management strategies that are robust to the uncertainty that require no forecast at all, and it would be to fish much more terminal areas, to have a lot more in-season management, not allocate the fish before you know how many are out there, and they do this in a lot of places. Alaska has been very successful with many of their fisheries for a century, and I think in our part of the world we're just stuck with a community of stakeholders that demand access to fish in the ocean from mixed stocks, from distant sources, and this presents a really big challenge for the management world where predictability is really low.
Okay, well, if you want my hero to switch back to the original name, all you have to do is advocate for that in front of the Pacific Council, and you will be my new hero.
All right. Let's take a 15-minute break so I know what to do about